Okay, welcome back after the festival season. So I hope you guys have been able to go through all the videos and uh, go through the lecture material. Now I noticed that the the viewership on YouTube, at least for the last video, which is lecture 6, was approximately half of the viewership for the previous lectures. So I encourage you to give me feedback. I mean, that could just be an anomaly due to uh, uh, due to the festival season, but I just wanted to make sure that you are being able to follow. I mean, it's a difficult semester for both of us, you and me. I have not had a chance to meet any of you, and you have not had a chance to meet me in person. And of course, there's nothing better than classroom teaching, where it's so much easier to clear doubts and make sure that most of us can be on the same page. But at this moment, when I am doing the recordings, which is sometimes late night, when everything is quiet, I'm trying to imagine a class in front of me, and it's a bit difficult to do that. And so I encourage you to please write to me, okay? And if you have any feedback you want to give about the quality of classes, or whether you are able to follow, not able to follow, if there's anything that can be done to improve it, I may or may not be able to incorporate all your suggestions, but I'll definitely try to do something about it. And please don't worry about you don't have to worry about if you write to me and whether I like it or not. Don't worry about all that. Just send me whatever you feel, and if there's any way to improve this. Okay, great. So let us do a quick recap. I mean, we have been through quite a bit of material in the last few classes, and one of the things that we learned now was the Lagrangian, or the material, or often called the substantial derivative. And the idea was that if you have a function, let's say t, which is now a function of time and the spatial location, then when I take the derivative of this t such that I intend to follow a fluid particle, then this becomes this expression on my right. Okay, so this was done in lecture 5, part 2, just in case you want to go back. Part 1 of 2, sorry, not the second part. And there's a subtle issue that I just wanted to quickly point out, and it is, what is this velocity that we are talking about? And this velocity, now the thing is, this velocity is the spatial velocity, but this velocity is also the velocity of a fluid particle. So if we have a fluid and you have this differential control volume set here, then what is, if I want to assign a velocity to this control volume, how do I do that? This control volume, since it is observer dependent, I can make this control volume fixed, and this control, even if this is a differential control volume, I can ensure that this is not deforming, neither translating. So what is this velocity u bar that one would associate with this? Well, the velocity you would associate with it is actually, see, the velocity is a Lagrangian concept. The only way we can understand velocity is by following a fluid particle. So if you were to imagine a fluid particle which at time t is occupying the exact same location as the control volume, then the velocity of that fluid particle is what we ascribe to the as the velocity of the control volume at that time. So that is a subtle issue, and that while this entire derivation was looked quite straightforward because it was just the application of chain rule, there is this subtlety that is underlying this derivation that we did. Okay, so I just wanted to point that out to you guys. Okay. Another thing to recap is the Reynolds transport theorem. Now, there are two ways to understand this, and the Reynolds transport theorem, the way the book approaches it, is through the Leibniz theorem and its 3D generalization, and then so it takes the 1D Leibniz theorem and then generalizes it in 3D, and that's where the chapter 3 ends, and then in chapter 4 it then goes on to apply it to different cases, and that's one of the best ways to understand it. But because of this peculiar situation where we are I would have been happy to use to explain Reynolds transport theorem through that method if we were in a classroom format. But since we are not, I felt that explaining it through that control volume formulation that we had done was somewhat easier. And what we found is, in that particular case, please remember that we had a fixed control volume. So the control volume that we had made, this CV, was a fixed control volume, not deforming, okay, or moving. So I have sort of fixed it to the frame of reference, and if both these conditions are met, then the equation that I got was, or we would get, is dB dt equal to the ddt of CV dB dm rho derivative of volume plus integral over the control volume dB by dm rho urel dot dA. Right, and when we are doing it, we said that this was equal to some beta, and that's how we did the entire derivation. And this is for a fixed control volume which is not deforming or moving. I mean, when it is moving, we are going to make some changes which we'll see later, but the formulation that we derived for the mass and even for the linear momentum uses the idea that is a fixed and deforming control, fixed and not deforming control volume, or not moving. And this method that I've followed is the reference text. If you want it, I'll just put it out for you, is Frank White's Viscous Fluid Flow. It's an excellent text for graduate level fluid mechanics, and here the way I derived it, the entire derivation is not done in the book, so the book sort of skips many steps, but finally we'll end up here as far as the Frank and White's book is concerned. However, the Kundu book uses the Leibniz theorem and the generalization of the Leibniz theorem to 3 dimensions, and that formulation is a bit the way the book Kundu approaches it, Kundu Cohen, that is more general, and that can be applied to deforming control volumes also. So that equation over there might look somewhat different than this. There is a partial derivative of time inside this integral in that case. And by the way, B is any extensive property. Okay, so B was an extensive property. Now, because B was an extensive property, we started out by assigning it certain values. So, so just doing recap right now, okay? And when we chose B as mass, and hence dBdm became 1 for that particular case, we got control of mass equation for a CV. Okay, and these are integral formulations, right? So we'll just write it for ourselves, just to remind ourselves. Later on we'll see the differential formulation of the same thing, but these are integral formulations. And then when we put B is equal to sum m into u, okay, then this ended up giving us the linear momentum equation, the LME for a CV. Okay. Now recall, and this is where we were last class. I think we were just here, right? So we just discussed this. This is the linear momentum equation for a control volume. So we had gotten till here, and here it is important to remember a few details. Okay, so tips. So one is that the LME is a vector expression. Okay, it's a vector equation. What does that mean? It means that there are 3 equations built into it, right, for the 3 dimensions that we have. So that equation can be broken up as f, just a second, let me just quickly see how I wrote it, f body, f surface, right? Okay, so I'll say f x, so wait a minute, I'll just say f body x plus f surface comma x is equal to the ddt over the control volume ux rho dv. So now I'm writing it for the ux momentum, the x part of the momentum equation, and if I were to do it for the control surface, then you have ux rho, you'll still have the vector relative velocity dotted with dA, right? Similarly you will have y, and similarly you will have z, right? I don't have to write it like that, but I just say similarly Okay. So there are two more equations, and this x subscript here indicates the x direction component. So if you have a y direction, you will just replace this x with y and this ux with ui, but this quantity remains the same. Similarly for uz, right? Okay. The other important thing here to point out is, remember, that u and urel are different. Okay. So I'll just quickly go back to the equation here. So here this quantity u bar, again a vector quantity, is different than this relative vector quantity. So what is this quantity? This quantity u is, if you have an inertial reference frame, and you have to have that for our basic equation to be valid, and let's call that capital X, capital Y, capital Z, then u bar is u bar x, y, z, which means that the velocity as measured with respect to this inertial reference frame. But the relative velocity, and urel is nothing but the velocity of the fluid with reference to this reference frame, once again, minus fluid velocity with respect to x, y, z, minus the velocity of the control volume with regards to x, y, z. Okay. So these two quantities, you can see, are different. Okay. And we can of course do LME for so these are inertial reference frames. So if the control volume is also moving in another inertial reference frame, it would, or with a constant velocity to the to an inertial reference frame, then it makes no difference and we retain the same expression. Okay. So if so our assumption is that the control volume is either at rest with respect to your inertial reference frame, or it has a constant velocity with respect to your inertial reference frame. If, however, the control volume moves with an acceleration with reference to your inertial reference frame, then we have to make a correction to this equation. We will see that in due time also. Okay. Now, in an exam, what you should do if you are solving these problems, good practice, okay, for an exam is, okay, now I have even more stuff. So let's say I'm just going to use Sanskrit numerals now. So draw the control volume that the equation LME, or sorry, the COM, which is the conservation of mass, or the linear momentum conservation equation, is being applied to. Okay. And for yourself, okay, indicate the reference frame x, y, z that is being used. There are multiple benefits of doing this, and one of the obvious benefits is that if you are making a partial mistake, then me knowing the reference frame that you have used helps me understand what equation you are writing and allows me to give you partial credits. If however you don't draw the control volume, you don't indicate what is the correct reference frame, then I am, and you make a mistake in the problem, then I'm groping in the dark about why you made that mistake, and I cannot give you partial points after that. So don't come to me later than the exam to explain what your assumptions were. Okay, so that brings me to the third point, which is clearly state assumptions. Okay, because it will be very, very helpful to all of us if you state that. It is helpful to you in the exam, it is helpful to me when I am grading the papers. So clearly state your assumptions, and if possible, draw your free body diagram. I mean, if possible or if required, right? Okay. And the other good practice is that the equation is quite cumbersome. So you might, I'm not going to write it down, I'm running out of space here. So you can write each term of a complicated equation, and then, so let's say you are writing the conservation of energy and that has so many terms. Just evaluate each term separately. It makes things simpler and concise, and it greatly reduces your likelihood of making a mistake. Okay, so just going over this all over again, draw your control volume. See, the control volume is dependent upon the observer. So you are the person who has to decide what the control volume is. Nobody is going to give it to you in the exam. Okay, so I'm not going to specify to you what the control volume is. You are free to choose a control volume as you wish to do. It can be a bizarre control volume as well, but if you choose the wrong one, well, my friend, you will be in trouble. Okay, so that if you solve enough problems, it will come to you as to what is the best choice for a control volume. But don't neglect to draw it, then it makes things so much more clearer to me. Indicate your reference frame, again helps you, helps me. Draw your free body diagrams if it's possible, helps you, helps me. Okay, so evaluate each of the, if it's a complicated expression, just evaluate each of the terms separately. Okay, for things like the control volume, the linear momentum equation, remember that there are multiple sources of forces. It's the body force, it's the surface. On each of the surfaces possible, there will be a force, which could be a normal force, for example pressure. It could be a shear force as well. Okay, for body forces, it could be, let's say, the weight, if the gravity is provided to you. If it's a electrical force, then if there's an electric field, there might be a body force due to the electric field. So there are different contributions to these different cases, and you have to make sure that you evaluate all of them. Okay, now what I have done with this in this particular case is and this I'm doing it for your sake, is that I am going to give you solved sample problems, and I'm not solving it in this lecture because I realized that it will eat up all my lecture time, and I didn't want to do that. So there are two sample problems that I have worked out for you, and I'm going to give you the entire PDF of that. And the first problem has there's a liquid film over a surface. So this is a wall and this is a liquid film. The height at any given location is given as hx comma t. This is x direction, this is y direction. The fluid can, of course, this is a two-dimensional problem, so the fluid can have u velocity or v velocity. U is the velocity in the x direction, v is the velocity in y direction. I mean, this is, by the way, quite conventional in fluid mechanics to use. I mean, I know that we are using u again and again, but this u is a scalar u, so I'm not putting any bar over it. This v is a scalar v, so there's no bar over it. And when you use scalars, then u is often used to indicate the velocity in x direction. and V is often used to indicate the direction in y direction. Z direction is often denoted by W. Okay, now the question is to construct an equation for conservation of mass governing this planar flow of fluid lying on a flat horizontal plane. It's given to you that hxt is the depth of the fluid. It's also given to you that that uxt, you can assume that uxt is independent of y, so there is no y here, and I've just written it down for you. That's how the wavelength of this flow is much longer than the amplitude. This is a sort of a shallow wave kind of a situation, so you can assume that the velocity in the x direction is much greater than the velocity in the y direction. So essentially you can neglect y, that's the point. Okay, so what I've done is I've already solved the problem. I've taken this problem and then I've drawn a control volume here. This is a differential control volume, although obviously it's exaggerated in my drawing, but this dimension is the differential part, but in this direction it's not differential. So it's, this height is finite h, and then the third dimension, which is into the plane of the paper, that's a unit depth, right? So the velocity, to evaluate this, what we did is we took the velocity at the center of this control volume to be u and the height to be h, and the mass flow rate hence is rho uh, and we have, this is the the equation for conservation of mass for the control volume, and then we just go ahead and evaluate all these quantities separately. This is the time derivative quantity. This is how it works out to be. Again, remember, this is a unit depth into the plane of the paper, so there is one more. So the volume dV, this is just the area h dx multiplied by 1. The 1 doesn't appear here. To find this derivative, what we have done is we have taken the mass flow rate at center to be rho uh, and then we have just done a Taylor series expansion of that, okay, for the left face and the right face. So that's why the left face is dx by 2 away from the midpoint, and the right face is dx plus 2 to the right of the midpoint. And when you evaluate all this, you should be able to come up with this answer. This is an often used equation in lubrication theory and thin films. This is an important equation. You might come across it later in some cases. Obviously, if rho were not a function of time and x, then you could take the rho out or drop it. So then you'll have a transient equation in h and u, right? So that is the problem. The second problem that we have worked out is that of a cart such that there's a jet velocity which is incoming as v jet. There's an area A that is given to you, and this fluid is coming in and just going out. Okay, this cross section here remains A. This is, by the way, this is just so the fluid just comes in and goes out like that. Okay, this area has nothing to do, there's nothing here as such. And pressure inside everywhere is PATM in the jet while it is in this cart. The entire cart has a mass m, and if you were not to do anything, then the cart would move with the velocity, okay, v cart, which is an unknown. And the question is, find Vx and so find the forces Fx and Fy if v cart were to be 0. Okay. So here again, the question is, you have to find out what, you have to figure out what the right control volume is by yourself, and you are the one who has to decide that. So we have drawn a control volume for ourselves here, and what you find out is you could either apply the integral equations for control of mass, or it is sort of obvious that since the areas are constant, this V out here, which is an unknown quantity, when the problem is being given to you, has to be equal to V jet, right? And then if you write the x direction linear momentum equation, then okay, I'm not going to go through this, but I've worked it out for you. Please take a look. This is the answer for the fx. I have not solved for fy, that I've just left for you. Okay. So this is going to be given to you, and that should be helpful. Okay. Now comes the other obvious equation, which is the equation for the angular momentum equation. Angular momentum conservation equation, of course. And let's just say we'll call it AME. Okay. Now, if I were to state in words the principle of angular momentum, then angular momentum conservation, then it says that the rate of change of a system's angular momentum is equal to, let's say, the net moment or torque acting on the system. What does it mean? Okay, so to understand that, let's maybe quickly draw an inertial reference frame. Let's say we have a body here and a system. Okay, so this is my system, and this is my inertial, so x, y, z. Inertial reference frame. Okay. So if I have a small amount, a differential control volume here, right? So let's say this is a differential control volume. Then how do you calculate? So let's say the velocity of this is given as u, okay, in the xyz reference frame. Then the angular momentum. Okay. Oh, one thing I have forgotten to draw. Wait a second. Okay. Maybe I'll draw. There are two things actually. Okay. So let's call this r, x, y, z, and I'll explain in a second what this is. Okay. So I have taken a differential control volume here, and that differential control volume has a velocity of u bar with respect to my inertial reference frame. It has a radius vector r x y z with respect to my inertial reference frame, and it has an h, which is an intrinsic momentum, okay, or intrinsic specific angular momentum of the piece of fluid, and that is given by h bar. Okay. So the principle of conservation of linear momentum, or sorry, principle of conservation of angular momentum says that the d dt, okay, and now you have to integrate over the volume of the system. And now the question is, what are the contributions of the angular momentum? Now you might be familiar with, okay, and I'm going to drop this xyz part. Okay, so you are probably quite familiar with the fact that the cross product of r and u contributes to the angular momentum of the system. But the system can also have an intrinsic angular momentum, which is not given by this r cross u term, and which is independent of that. And this intrinsic momentum here I have already written as h bar. So the total angular momentum of the system is a contribution of these two quantities, one being the intrinsic specific angular momentum. This usually results from the fact that molecules can have their own spin within a small fluid differential volume, and this kind of angular momentum can exist for fluids such as magnetic fluids and polar fluids, and when, let's say, if the particles have a dipole and there's an imposed electric field which is making them orient a certain way, so there is a non-zero specific angular momentum. But for most fluids, okay, you can sort of neglect this term. Okay, but before that, just a second, I think I should write what is on this side. So this is the moment or torque. Okay, some people use T, or so you can use M. It's all the same on system. Okay. So as I said, H, X, Y, Z is the intrinsic specific angular momentum. This H bar is the reason why, I mean, I don't know if it has happened to you, but when I was in school, there were all these horrendous problems which asked us to derive angular momentum equation from the linear momentum conservation equation, and they would just use the linear momentum conservation and then do an R cross, and then voila, you have the angular momentum equation conservation. But that's not correct, because the angular principle of angular momentum conservation is an independent conservation equation, and H bar is the reason why that is there, because there's a specific angular momentum term that doesn't come through this cross term. Okay, so for most quantities, for most real fluids, for most systems such as water, air, this H bar is 0. Okay, so for most fluids which are non-polar and non-magnetic, the individual molecules, they orient randomly, and finally all this angular momentum, intrinsic angular momentum, basically sums up to 0. So one can easily neglect the contribution of this quantity, and then the only quantity that is acting and contributing to this is the U term, R cross U term. Okay, so if you have this, so if H bar is 0, okay, then this is the only contribution to the angular momentum, and then you can safely say that, or choose B to be R cross U. Okay, and once you do that, then you know that your, just like the previous case, your M body, so the momentum as a body force and momentum on net moment due to body forces, and the net moment due to surface forces on the control volume, that is be equal to d dt of R cross U rho dV, this is control volume, plus integral over the control surface R cross U rho urel dot d. Okay, and this becomes my important equation. So so this quantity, the first quantity here, this is basically giving you the rate of increase of angular momentum inside the control volume, and the second term here, this is the net rate, this is the net rate at which the angular momentum changes due to flux at the control surface, right? And as I said before, the first term here, this represents the net moment due to the body forces acting on the control volume. The second one is the net moment due to surface forces acting on the control volume. And in the simple case that that the moments are just due to forces, then your M, in that particular case, your M body is basically nothing but R cross F body, and M surface, I should have put Z vectors. Okay, so just remember that there can be certain cases where, for example, magnetic fluids, where there could be additional moments that induce the change of momentum, angular momentum inside. Okay, so if you don't consider those cases, then this is the simple equation for conservation of angular momentum for a fluid. Okay, so that leaves us with the principle of conservation of energy. Okay, so what I'll do is I'll start over with the conservation of energy, of course, for a CV. Okay, so we'll just end it here. This is where we're going to start off in the next lecture. Okay, so I'll just end it here now.